Thank you.
Was yours.
I'll be presenting for Sadie. Sadie did these experiments, and I analyzed the data before he worked with the data collection. In the interest of time, I'll skip some of the introductory stuff. People have long looked at energetic charged particles from metal hydrides, metal deuterides. In our experiment, we've got a DC25 ion source, can give us up to about 1 kilovolt ions that can do hydrogen, deuterium, argon. We have a vacuum chamber. Okay. So if you so there's an ion source here, comes into a target. The target's red, it's at an angle here. And the blue here is an array of charged particle detectors. And this is what our experiment looks like from the outside. Okay, so a lot of people think that the problem is to detect LNR charged particles. But in a sense, detectors have been around for a long time. They work very well. The real problem is how to make them. And so the idea here is we'd like to make D2 in the lattice. So if you have bulk palladium or bulk titanium, you don't get D2 because the D wants to be in palladium, it wants to be in octahedral sites, and titanium wants to be in tetrahedral sites, so you don't get double occupancy. So in palladium, we need monovacancies. Since the background electron density is too high at those sites, we expect the same thing needed in titanium. In palladium, if you load palladium near unity, you reduce dramatically the vacancy formation energy. It takes a lot less energy to pull a palladium out and make a vacancy. We expect the same kind of thing happens in titanium. We'd like optical phonons to stimulate the transitions, sort of like my theory talk. We expect optical phonons to be generated by the ion beam, and we also expect deuterium flux, either due to heating or outgassing or whatever, will also make optical phonons. So the conceptual protocol, we start by loading deuterium into the titanium at low power to keep it cool. We'd like high loading near the surface, and titanium can load up to titanium D2. After the loading, we want argon bombardment to make monovacancies. And we'd like high energy and a lot of bombardment. This bombardment can also heat the sample near the surface and cause diffusion and outgassing, and it can also make terahertz vibration. And then after the argon ion beam is turned off, the sample can also outgas, which can stimulate transitions. So I want to start with the thick film titanium experiments. So we started out with thick films, and we had 500 micron thick surface silicon barrier detector looking normal at it. So here's a time history. So down here, okay, the blue line is gas flow. The purple line, the higher line, is the ion current. So we had an ion current at looks like about 0.5 milliamp of deuterium loading the sample. And then we stopped the deuterium loading and switched over to argon bombardment. And in this case, coincident with the argon bombardment, we got 4 counts at very high energy. I'll be commenting on this very high energy. Needless to say, our detector was not calibrated at that high energy. Going into the experiment, we've been hoping to see the 5 MeV particles that had been reported by NRL in the early 90s. and we had MRECM241 source to get calibration. So the question is what happens at higher energy? Well, in previous studies of SSB detectors with thick detectors, the pulse height is linear in the energy up to quite high energies. And so if you do a calibration at low energy, your calibration is not going to be good at high energy. On the other hand, it's not the case that you have no information at all. So this is something we've been scratching our head about. The range of an alpha particle in a 500 micron thick silicon surface barrier detector is about, you can absorb the energy from about a 32.5 MeV alpha particle. At higher energy, your energy deposition is incomplete. For a proton, you're about 8 MeV or thereabouts. So whatever's giving these signals of high energy, they're certainly not protons or other light particles, presumably helium-3 or alpha particle. Here's a SRAM calculation of the deposit energy as a function of incident alpha energy. So we have a 2,000 micron silicon surface barrier detector that we use in the thin film experiments I'll describe shortly. We have, for the 500 micron R-series detector, the energy deposition at normal incidence, it peaks at 32.5 MeV and then goes down. So for signals under 32.5 MeV, we don't know which side of the curve that we're on. Okay, so for the data that I showed you before, we had a Wendy 2 medical neutron detector right outside the chamber, and we saw extra counts, time correlated with the energetic particles that came in. This is another experiment that was basically fairly similar. The intent was to try to replicate the earlier measurement. So we have deuterium loading going on here, a little bit more than 1 million, and then wondering, I think I've got the labels backwards here. The purple here, which is labeled as deuterium loading, is the outgassing, it's the gas flow. So down here, so this is backwards. But with the ion bombardment, we get the gas flow, and we get argon, or energetic particle that the detector registers as having a little bit less than 30 MeV, again with our imperfect non-calibration high energy. So thinking about the experiment so far, we'd hoped to see energetic ions near 5 MeV. We were completely astonished and stunned that the energetic particles were so high. The effect looks real, it looks weak, and what we really need is more signal, and we also need calibration high energy. We need particle identification. We subsequently tried experiments with a 5 micron thin film. So the idea is that if we have, says 25 microns, it was actually a 5 micron titanium target. So it was on top here, we were able to bring our 2,000 micron thick silicon surface detector right behind it, which provides a big improvement for steradian coverage. There are other issues as well. We found we needed cooling because under the argon ion beam bombardment, the detector would heat up and make the pilot go up. So this new configuration follows what was done at NRL in the early 1990s and has been done elsewhere. We worked with a very thin sample. Again, thinking about NRL. NRL worked with a sample of roughly 2 microns thick. And we wanted to minimize the energy loss. From the SRAM code, here's DEDX times 5 microns. So you have very high energy, we don't lose much energy at all. Low energy, we lose a little bit more. So these are for alphas going normal through 5 micron titanium. Here's the first experimental result from the new detection system. And I thought this was an important one to show. Here, the data points as a function of channel. I've got an algorithm, I've got sort of an infinite number of data points, so I have something going search for the top of the pile up. So this is the top of the pile up being shown, and you should imagine underneath there's just completely filled with an exponentially growing number of counts. For the first part of the run, loading was done with deuterium at considerably less than a milliamp. And then after 12 hours of loading, we ran with the argon ion bombardment, also 950 eV ions. And as you can see, over the entire over the entire experiment here, there are no counts whatsoever above pile up. So the background noise is above pile up is low. Okay, so here's an experiment. This was done before the cooling was put in. So this is again the algorithm to figure out the peak of the pile up. And so the detector warmed up a little bit, so the pile up went high. The scale's different. On the other one, we went up to 16,000. And here we're only going up to 2,000, so you get to see much better what's going on at low energy. But here we get some counts in the 3 to 6 MeV region, correlated with the argon ion beam bombardment. The time scale here is funny. It's 2,000 seconds in connection close up with the argon ion bombardment. And then afterwards, this is 2,000 up to over 80,000 seconds, more than 24 hours of no counts whatsoever in this region. Let me go to another, well, the issue here is we're thinking that maybe in this data we were getting counts somewhere near 5 MeV, and perhaps these were at shallow angle, and we were getting more energy loss. So maybe we were seeing what NRL had described previously. Here's another experiment, again with a thin foil target. In this region here, this is the end of the deuterium beam loading. And then we do our argon ion beam bombardment. Here we get an energetic charged particle. The detector calibration, after looking at the data at high energy for this thicker detector, even though by channel this is reporting up over 45 MeV, I think that this is, if there's consistency between the ion energies and we're on the other side of the curve, this probably should be down closer to 40 or 42 MeV. Then after the beam's turned off, again, this is a different time scale, much longer time scale. At the bottom, we see emission between 2 and 10 MeV that lasts for a while, and then it turns off, and there's nothing that happens afterwards. So the thought is that perhaps outgassing, perhaps radial diffusion of the deuterium might be causing the vibrations to give us signals out there. Okay, think a little bit about mechanism. So I described nuclear molecule model. Here's what happens when you have titanium. There's fewer states, far fewer states than there are for palladium, so the density of states is lower, which means to me that titanium's a much better candidate for energetic charged particles or loss in general. If I think about a similar kind of mechanism in titanium. If I go from D2 to compact D2, then perhaps I can go up, but there's fewer binary states up here. Excess heat's been reported in titanium, so there may be ternary or four body states or something to make there be more to support excess heat. But the idea is that we start from D2, go to D2 compact, and then here, it's not so much that there's long-lived resonance states here, but instead, there's going to be unstable states. And if we couple to the unstable states, then we can get energetic charged particles, which is ground state titanium plus 24 MeV. And here are the candidates that we get. So we get deuterons between 3 and 6 MeV. We get helium-3 and helium-3 tritons down up to 5 MeV. I actually think this guy right here is the candidate that would be connected with the NRL measurement, and then alphas of higher energy, protons of higher energy. And in some sense, this spectrum of stuff kind of is related to our low energy signal. And then if we go up to 2 delta E through the mechanism I described before, then we would hit here, we'd get a range of different nuclear molecules with a big spread in C. Now, because of the recoil energy dynamics, there's no way that these guys can give you energies above 30 MeV. The only possibilities are with protons and alpha particles. And if the signals are the same in the earlier experiment with the thinner detector, and the thicker detector, then that means we're thinking about alphas up here. And the more energetic thing up over 40 MeV basically through this mechanism, couldn't be from titanium, have to be from something a little bit heavier. Anyway, to summarize, we're thinking that the 1 delta E would give us this, and the 2 delta E would result in alpha particles 34 to 36 MeV, which would not be a bad fit to the data. So we got some positive results. There's more data. There's something like 8 or 9 observations of the high energy 30 MeV plus signal, and there's 7 or 8 observations of lower energy particles. We didn't, with a larger area steradian coverage of the close detector, we had hoped to see a higher count rate, but we didn't. And what that means is that the 5 micron target just simply isn't as good at providing a source for the low-level energetic charged particles. So what we're thinking of is going to a thicker, maybe 20 microns, 25 microns or so, and we'll have a little bit more energy loss, but if we want to focus on the very energetic charged particles, that should be acceptable. But that should give us more of them. We now have a new, larger area, 9 times larger area, which should get our count rate up, especially with a little bit thicker target. We've got a thin DE detector ordered, which will be most useful for the 1 to 11 MeV particles. And then I located, forget if it was UC Davis or something, but there's a facility in California that's capable of doing calibration of silicon surface barrier detector in the 30 to 40 MeV range. So we have the prospect of actually establishing a calibration of the higher energy. Thank you.
Any questions for Peter?
No questions, I'm off the hook.
Okay, this is the end of the session. The lunch is...
Sorry?
Hey,
Ready?
hold on, you said are there any questions? And I said I haven't.
Oh, sorry, I didn't hear. I apologize.
Sorry, I can be even louder in the back there. Peter, just a quick question on the last graph of data where you had one count up at around 40 MeV, and then you had a bunch of counts that lasted for a period of time on a nonlinear time scale. That one.
Yeah.
Yeah, so about how many, one day is about 50,000 seconds, right? So that's, I just wanted to make sure that's not cosmic, the background stuff that is on the nonlinear scale there in the back.
Okay, 250,000 seconds, that looks like.
Well, that would be about 12 hours is only 50,000 seconds.
3 days or something like that.
Okay, so it can't be, it's just, right, okay.
Good.
Yeah, it's better to show the spectrum itself because we don't see the effect of noise. That plot doesn't look like nice. I mean, for me. But anyhow, my question is, let's say, you are now employing the delta E detection to make sure these are the real particle and some of the you want to identify what the particle is. Yeah, so it is. Yeah, I recommend that should be. I will wait for if you get the data from this experiment. But
in terms of the time history here, there are a small number of publications of people that did experiments previously, and that's what their data looks like. So reproducible few counts.
yeah, but if you interpret this is the kind of decay of your very high state of titanium or something else, you want to interpret this is the decay of a long life state.
No, not at all.
Because you still have this count.
The beam is turned off in this later time. So the thought is that the sample is changing or bending. It might be outgassing. There might be slow diffusion of deuterium out, and that's what's sourcing LNR effect to give us this. That's the picture. It's not a decay of an excited nuclear state.
That is the one. So if you are during the argon impinging, you have one count over there. Yeah, that is your event looking for.
I'm sorry, I can't understand you.
Sorry. The event over there, which is you want to interpret as a decay of your molecular state.
It's not so much what we wanted. We just the detector stayed on. This is what showed up.
Any other question? Well, let's thank Peter and Sadie.